All right, hello and welcome to this Thursday evening's chem lecture. We are going to continue with our discussion of titrations. First off, we're going to do the problem that I left the class with at the end of last lecture. And then we're going to kind of finish out our discussion of titrations we're going to do a few more examples, but we're also going to kind of flesh out conceptually how titrations relate to our final two lab modules, 11 and 12, I believe, are the numbers. And so we're going to kind of talk about conceptually what's going on in those, and then do some math, some problems related to those. But first, let's go ahead and do the example that we left off with on Tuesday. So first, KHP is an acid. We'll be talking a little bit more about KHP in a moment, that reacts with sodium hydroxide in a 1-to-1 ratio. Our initial volume of sodium hydroxide is 1.03 milliliters. Our final volume is 14.96 milliliters. This volume of sodium hydroxide was added to 25 grams of KHP dissolved in 20 milliliters of DI water. Determine the molarity of sodium hydroxide, because that's what the square brackets mean. Now, the first thing I want to point out, and those of you who got started early on the lab exercises, several of you have asked me about this already, and so for those of you who haven't, FYI, this part right here, where it says 25 grams of KHP was dissolved in 20 milliliters of DI water. I think it was like 25 in the lab exercise. This is extra information. You do not need this to solve the problem at hand. And so that's not typically my writing style. I don't put extra information in there. But they did in the pre-lab, so I wanted to do an example where there was some extraneous information. We're not actually going to be using that because this is just a volume of water used to dissolve our acid. But what matters is that our acid is going to react with sodium hydroxide. All right. So let's break this down. I'm going to need to zero out this page. So we have a little bit of room. So I have a little bit of room to write. Now, first off, we are trying to find the molarity of sodium hydroxide, which molarity has an equation. We should write that out because that'll provide us a roadmap for solving this problem. Molarity is equal to moles of sodium hydroxide over the volume of the solution in liters. Now let's look at what we're given. First, we're given an initial and final volume. Right, our final volume is 14.96 milliliters. Our initial volume is 1.03 milliliters. So our volume of sodium hydroxide is going to be final minus initial, which comes out to be 13.93 milliliters. All right. This is, right here, our denominator. But it's not enough to know the volume. We need to know the volume in liters. So we actually have to do a unit conversion here. We want to cancel milliliters. We want to be left with liters. 1 liter is 1,000 milliliters. So our volume of sodium hydroxide in liters is 0.01393. All right, we've got our denominator. Halfway there. We just need to find the numerator, all right? And the piece of information that we're given is we're told the mass of KHP, right? So there's a little, sorry, given part 2. So we're told that we have 25.0 grams of KHP. We're also told that it reacts in a 1-to-1 ratio with sodium hydroxide. So if we knew moles of KHP, we could convert to moles of sodium hydroxide. And thing is, KHP is an acronym. It's not a molecule with potassium, hydrogen, and phosphorus. And I didn't actually make that, I didn't explicitly state that in the problem. So if you made that mistake, I apologize. But also know that if you made that mistake, you still fundamentally understand how to solve this problem. So even though your numerical value will be different, you still understand the process, and so you're golden. You're more than fine when it comes to being prepared for the exam. The molecular weight of KHP is 204.22 grams per mole. So mass cancels. Next, we need to convert moles of KHP to moles of sodium hydroxide. And we were given that this is a 1-to-1 mole ratio. So moles of KHP cancel. And now we're ready to crunch our numbers. 25 divided by 204.22 times 1 divided by 1 is, let's see, 3 sig figs, 0.122 moles of sodium hydroxide. And now we can calculate our molarity because we just need to divide our moles by our volume in liters, which is 0.01393. Punching it in, we get a very large molarity, 8.76, rounding to 3 sig figs. Would be the concentration of sodium hydroxide in moles. All right. So that is the answer. Again, if you tripped over the molecular weight of KHP, I apologize. But if you set up the calculation correctly, you're good to go. All right. So let's take a moment and talk a little bit about kind of a user's guide, what you need to know conceptually, background wise, um, to to kind of unpack um, our final lab exercises. All right, so um, as we know, a titration is an experiment used to determine the concentration of some solution. All right. So, for example, um, vinegar. If you go to the store and um, buy a bottle of vinegar, it doesn't matter what kind. It could be white distilled, could be red wine vinegar, it could be apple cider vinegar. Vinegar, your garden variety vinegar, is advertised as having a percent mass of acetic acid of 5%. So if you pick up a bottle of vinegar, it'll say 5% acetic acid, and that is a percent by mass. We can use titrations to verify whether or not this advertised percent concentration is correct. All right. So here's the thing. If we are going to determine the concentration of acetic acid through titrations, then what we need is a standardized solution of base. We're going to need a standardized solution of some base to use in the titration with acetic acid. Standardized is just a fancy word. That means that it has a known concentration. All right, if you don't have a solution of base lying around, you're going to need to make one, standardize it, right? Determine precisely what that concentration of that solution is, and then you can use your standardized solution of base to determine your percent concentration of vinegar. So, sorry, I'm just repositioning it. Okay. So what you're going to be doing, so these are the steps involved. Step 1. Standardize a solution of sodium hydroxide. In other words, our goal here is to determine the molarity of our sodium hydroxide solution. Once you know the molarity of your sodium hydroxide solution, second step is titrate sodium hydroxide with vinegar. And then step 2 or 3, it's kind of the same. I'm just gonna roll them all. Titrate sodium hydroxide with vinegar and calculate the percent concentration of vinegar. I don't know why I wrote it with an E here. All right, now, to accomplish these steps, starting with step 1, we need to titrate our sodium hydroxide with a known amount of acid. Now, this might start feeling a little circular to you. You might be looking at this going like, wait a minute. Let me get this straight here, Josh. We have an unknown concentration of acid, so we need a solution of base. But to determine the concentration of that solution of base, we need to react it with a different acid? The answer is yes. You're like, isn't that circular? No, because this acid right here is not acetic acid. It's a different acid, and that acid's name is potassium hydrogen phthalate, or KHP. All right, so we're standardizing sodium hydroxide. Potassium, hydrogen, phthalate is potassium is KHP. You're like, wait a minute, what KHP? Yes, because potassium is the has the chemical elemental symbol K. All right, so this molecule, potassium hydrogen phthalate, looks like this. It's a big organic molecule. Excuse me, I'm so sorry. There's the potassium cation. This entire molecule, the reason we use it for several reasons. One, it's a solid. It's a solid. It's easy to handle. It's easy to weigh out. It's not a very strong acid, so it's not dangerous to use. It's a solid, so it's easy to use. And there's only one hydrogen. You can look at the rest of this molecule as just being A. So conceptually in your mind, KHP, this is what it looks like. You're not going to get tested on it. Don't worry. But it is literally just HA, and it reacts with sodium hydroxide to produce water That's where it's acidic. Hydrogen goes, plus sodium, and the rest of it. All right, this is the reaction. What's important here is that we have a 1-to-1 molar ratio, and that's going to be critical for our calculations. You don't need to know the structure of this guy. You do need to know its molecular weight. It's rather large. As we talked about in the last problem, it's 204.22 grams per mole. All right, so that's potassium hydrogen phthalate, KHP. And this is the reaction, the acid-base reaction, for the standardization step of this experiment. So let's do an example. All right, so for example, 10.2014 grams of KHP is used to standardize a solution of sodium hydroxide. The initial reading on the burette was 0.50 milliliters. The final reading on the burette was 42.20 milliliters. Determine the molarity of sodium hydroxide. All right, so we have to calculate this situation. As we've seen before, it's useful to write out the equation for molarity. Molarity is going to be equal to the moles of sodium hydroxide over its volume in liters. And just like the previous example, actually, we're going to determine our moles of sodium hydroxide using the mass of KHP, and we're going to determine our volume in liters from the initial and final volumes given. All right, so let's go ahead and start with volume because it's easy enough to line up. Final volume, 42.20 milliliters. Initial volume, 0.50 milliliters. Take the difference between these two. You're gonna get 41 something. Yep, 41.70. We got to keep that 0 there because sig figs wise, both of these numbers have their last significant digit in the second decimal place. So we have to have our last significant digit there. So 41.7 would be incorrect. Finally, we need to convert this volume to liters. And 1 liter is 1,000 milliliters. So our volume in liters would be 0.04170 liters. And that is going to be the denominator of our calculation for molarity. Now we need to determine the moles of sodium hydroxide, and we can do that using its molecular weight, which is 204.22 grams of KHP are in 1 mole. And then finally, we can convert from moles of KHP to moles of sodium hydroxide. Because, as we saw in the previous slide, the ratio from KHP to sodium hydroxide in the balanced chemical equation is a 1-to-1 ratio. Okay. So now we can crunch our numbers, find our moles of sodium hydroxide. We have 10.2014 divided by 204.22 times 1 divided by 1 comes out to be 0.0499. Oh, let's see. 5299. When you look at the number of moles sig figs we can keep. Our mass has 1, 2, 3, 4, 5, 6. And our molecular mass has 1, 2, 3, 4, 5. So we can keep 1, 2, 3, 4, 5, which means this 9 rounds up. So this is 0.049953 moles of sodium hydroxide. All right, now we can calculate our standardized molarity of sodium hydroxide. Because we take our moles of sodium hydroxide, 0.049953 moles of sodium hydroxide over our volume, 0.04170. Let's see, 0.04, now we crunch our numbers, 9953 divided by 0.0417. This gives us a molarity of 1.1979137. You'll notice that our numerator has 5 sig figs. Our denominator has 4, so we have to round to 4. 1, 2, 3, 4. This 9 rounds up. So our molarity of sodium hydroxide is 1.198 molar. That is the standardized solution of sodium hydroxide. Standardized is just another word of saying certainty of its concentration. Now, if we were doing an actual standardization, like if you're doing this in lab, you would not base your standardization off of one calculation. You'd actually do this in triplicate. You do 3 different titrations with your solution of sodium hydroxide and KHP, and then take an average of the 3, and that would be the molarity that you'd use to calculate it. Your percent mass of acetic acid and vinegar. All right, so that is the standardization. This is what really the pre-lab 11 and in-lab 11 are all about, is the standardization titration. So that has you set up there. Now, the second stage of this, we're going to use we're going to use the concentration of molarity of sodium hydroxide that we calculated here to determine the percent mass of acetic acid in vinegar. And we're going to do that by solving the following problem. But first, Brianna. Okay, great question. Do we get docked down if you put a 0 at the end? And I guess before I answer that, did you mean a 0 at the end of the molarity of sodium? Oh, okay. Sorted itself out. And this is going to be the titration of vinegar with our standardization of sodium hydroxide. Okay, no, totally no worries. Okay, so let's look at this next example. It's kind of a part 2. Okay. And this is the reason why we did the standardization. So 1.18, oh, sorry, 198 molar sodium hydroxide is titrated with 10.00 milliliters of vinegar. Whose active ingredient is acetic acid. The initial volume on the burette reads 1.20 milliliters. The final volume on the burette reads 7.92 milliliters. Part A. Determine the molarity of acetic acid. What is the molarity of acetic acid? Part B. Part B, use the molarity of acetic acid. And its density which is 0.9600 grams per mil, to determine the percent mass of acetic acid in vinegar. Then part C. How does our calculated percent mass compare to the advertised mass? Percent of 5% acetic acid. All right, so we have a few things to figure out. First and foremost, we need to find the molarity of our acetic acid solution, and we're going to do so in a much similar way. So, and sorry, I've got to blank this whole page, but part A, we're trying to find the molarity of acetic acid, right? So this is equal to moles of acetic acid over its volume in liters. Now, we're told what volume of acetic acid that was used in this titration. We're told that 10.00 milliliters was used, right? Again, we have to do a unit conversion there. But that's where the denominator comes from. The numerator is going to come from the reaction of acetic acid with sodium hydroxide, and we're going to need a balanced chemical equation before we can do that calculation. So acetic acid reacts with sodium hydroxide. This is a neutralization reaction. So our products are going to be water, and the ion from our metal hydroxide is sodium, +1 charge. The anion is acetate, one of our polyatomic ions, which has a charge of -1. So because we have an anionic charge of -1 and a cationic charge of +1, these are going to combine in a 1-to-1 ratio to make sodium acetate. Now, if you look, this equation is already balanced. We have 1 sodium on either side. We have 2 carbons. We have 1, 2, 3, 1, 2, 3 oxygens, and then we have 1, 2, 3, 4, 5 hydrogens, 1, 2, 3, 4, 5. So it's already balanced. And the critical thing here is in this balanced chemical equation, we are dealing with a 1-to-1 ratio between acetic acid and sodium hydroxide, and that's what we need to do our unit conversion. All right, let's find our moles of acetic acid. We're given the molarity of sodium hydroxide, which we know is equal to moles of sodium hydroxide over our volume in liters. We're given molarity. We're given initial and final volumes, so we can find our denominator. So to find our moles of sodium hydroxide, we need to multiply both sides of this expression by its volume in liters. So we get a new expression. Moles of sodium hydroxide is equal to the molarity of sodium hydroxide times its volume in liters. This volume comes from the difference between our final and initial volumes. So our final volume, let me find it real quick, was 7.92 milliliters. Our initial volume was 1.20 milliliters. So this comes out to be 6.72 milliliters is our volume. So now we can find our moles of sodium hydroxide by multiplying our molarity, which is 1.198. And now, instead of writing that big M, I'm going to split it into its numerator and denominator. It's moles of sodium hydroxide in the numerator over liters times. Oh, snap. We know what our volume is. But we got a problem. It's in milliliters, right? So we got to actually do a quick unit conversion here, because we need to know how many liters of sodium hydroxide reacted. So this comes out to be 0.00672 liters, and that's what we should be using here. And now liters cancel, and now we can convert moles of sodium hydroxide to moles of acetic acid, and this is a 1-to-1 mole ratio from our balanced chemical equation. So let's crunch our numbers here. 1.198 times 0.00672. Let's see, is 0.0080506. But I can only keep 3 sig figs, 0 rounds down. So we have 0.00805 moles of acetic acid. Okay. Now, moles of acetic acid is the numerator. We have our denominator. Granted, we need to do unit conversion there, but we're almost there to the answer for part A. Quickly, 10.00 milliliters converted to liters comes out to be 0.01000 liters. So our molarity of acetic acid is 0.00805, that's moles. Of acetic acid over 0.01000 liters. All right, and that is the answer for part A. That is the molarity of acetic acid. All right. Now, part B of this problem asks us to use the molarity that we found in part A to determine the percent mass of acetic acid. All right. So for part B, we are being asked to find the percent, oops, didn't mean to do that in purple. The percent mass of acetic acid. All right, now to do this, anytime you're asked to find a quantity that has an equation associated with it, it's worth your time to write out what that equation is. And the equation for percent mass is grams of solute, so that's grams of acetic acid, over grams of solution times 100. All right, now what we're given here we're given a molarity, which we just calculated, which is 0.805 moles of acetic acid over liters of solution. Now, I hope you can see that really the difference between percent mass and molarity is more or less a difference in units. For example, molarity has moles of solute in the numerator. Percent mass has grams. Well, we can convert from moles to grams using molecular weight, right? The denominator has liters of solution for molarity. Denominator has grams of solution for percent mass. We can convert between volume, from volume to mass, using the density. All right, if you know the density of your solution. Really, then the only actual difference is this goofy times 100 that makes it a percentage. So if you convert your denominator from volume to grams and your numerator from moles to grams, then you just multiply by 100 and you've got your percent mass. That is exactly what we're going to do here. I'm going to just scoot this down because this calculation is going to get a bit long in the tooth and I need every inch of page space. So first, hold up. There we go. First, we want to convert from moles of acetic acid to grams. So we have a molecular weight to calculate. Let me sidebar that right here. So carbon has an atomic mass of 12.01, hydrogen 1.008, oxygen 16.00. There are 2 oxygens in this molecule. There are 4 hydrogens, and there are 2 carbons. So we have to multiply each of these numbers accordingly. That was my best silent sneeze for you. Caught on live stream. All right, so let's see. 1.008 times 4 plus 32 plus 24.02 gives us a molecular weight, of 60.052. Our last sig fig is in that second decimal place based on the numbers I was using. So there are 60.052 grams per mole for acetic acid. Next, you'll notice that the density that we were given is hang on, so real quick, the density we were given for this solution was 0.9600 grams per milliliter. All right, per milliliter. And the volume of this solution is in liters. All right, so we need to convert from liters to milliliters if we're going to use our density properly. Whoops. All right, so 1 liter is 1,000 milliliters. So liters cancel milliliters. Now that we have milliliters in the denominator, we can use our density, which we want to put milliliters in the numerator to cancel, and 0.9600 grams in the denominator. So milliliters cancel milliliters. Moles of acetic acid cancel moles of acetic acid. We're ready to crunch some numbers. So we have 0.805 times 60.052 divided by 1,000 divided by 0.96. Comes out to be 0.0, let's see, we're going to be limited to 3 sig figs. 0.503561. You count off 3 sig figs, 5 rounds up. So this would be 0.0504. Now look at the units that are left over. It's grams of acetic acid. Oops. over grams of solution. Now, this is the easiest mistake to make when you're doing a calculation like this. The easiest mistake to make is to just box this. But remember, what makes this a percentage is multiplying by 100, and we haven't done that yet. So to get our percent mass, we got to multiply this number by 100. All right, so finally, our percent mass of vinegar based on our titration and standardization comes out to be 5.04%. Now, the last step in this problem asked us to compare our calculated value to the advertised value, which the advertised value was 5%. And I would suggest to you that these two numbers are the same. They just have different precision. Notice that if you took our calculated percentage and rounded it to the ones place, what would it round to? The answer is 5%, right? So the advertised value actually is accurate, is correct, but it's less precise than our 3 sig fig answer, which tells us that this batch of acetic acid happened to be 5.04% by mass. Now, there's a reason why the people who sell vinegar report it only to the ones place. Because there's going to be a slight variance batch to batch. So you might have some that are slightly less than 5%, some that are slightly higher, but all of them, when you round to one, not even one decimal place, the ones place, still comes out to 5, and so they can't be accused of false advertising. If they're saying it's 5% acetic acid, but it actually came out to 3.75, that would be false advertising. But they actually use sig figs to account for the fact that they don't have precise control, that there's some variation batch to batch, product to product. All right. Nothing like starting lecture with a 45-minute problem, right? But having done this, you will be well prepared to tackle the last remaining problem in the last remaining lab exercises for the semester. So this really gives you kind of the a conceptual background for tackling those, as well as kind of a nuts and bolts. Here's some of the calculations that you're going to have to be doing. So hopefully you find it helpful. All right. We only have one last topic to cover in Chapter 10. And that is the topic of buffers. But before we get there, we need to talk about acid-base strength. Okay, so let's talk about acid strength. All right. So, I started the discussion for this chapter talking about how acids are, it's a scary word, right? Because, you cut the xenomorph in Alien, it bleeds, its blood is acid, and it eats through your ship's hull, right? But I said not all acids are that gnarly. I mean, we just did a 45-minute long problem that was all about vinegar, which has acetic acid in it, and we use that to make salad dressing and stuff. So not every acid is terrible. We even know water's an acid, right? So this is something that's been implicit in our discussion, and in our discourse, in our dialogue all chapter long, is that different acids have different strengths, and part of an acid's strength can come from its concentration, right? The more concentrated something is, the more dangerous that particular solution is. If you have something that's very dilute, it's not going to hurt you at all. If you have something that's very concentrated, then it can deal some damage. You can get some acid burns. But that's not the only factor. It turns out that some acids are very aggressive, even in small concentrations. They just protonate very aggressively, whereas other acids are a little more reluctant to protonate. And we have ways of rating how strong an acid is. And they all come from the equilibrium for the reversible reaction when a generic acid reacts with water. All right, so our rating for acid strength is based on the acid ionization equilibrium. All right, the acid ionization equilibrium. So, when we talk about acid ionization, we're talking about a generic acid, which I'm going to call HA, reacting with water. Oops, water's not aqueous. Water dissolved in water. It's just liquid water. The products of this equilibrium will be aqueous hydronium and the acid's conjugate base. All right, so this is the equilibrium. Now, if you write the equilibrium constant for this reversible reaction, we say that it's K, and this is called Ka because it's the equilibrium constant not just for any equilibrium, but just for a specific equilibrium, the ionization of an acid. So the Ka of an acid, we can write that equation out. It equals the concentration of its products over its reactants, right? Hydronium times the conjugate base of the acid. I don't need to put the phase there. Over the concentration of the acid. And again, water is not a part of this it's part of the equilibrium, but it does not influence the equilibrium constant because the concentration of a liquid is constant. It's not going to change over the course of the reaction. Okay. Sorry, I lost where I was in the notes. Okay. Now, excuse me. Um, these numbers tend to be have very very dramatic exponents um, when you calculate them. Um, it's usually some number times 10 to the negative, could be as small as -3, could be as out of hand as 10 to the -10. So there's a very large dynamic range in which these fall. Well, actually, before I get there, first, let's think about what this means for a hot second. We have concentration of products over the concentration of reactants, just like we do with all chemical equilibria, right? It's products over reactants. That means that large Ka, a large value for Ka, means there's more products, which in turn makes for a stronger acid. Right? The larger the value of the equilibrium constant, the stronger the acid. Now, as I mentioned, the values for Kas there's a very wide dynamic range. And so to mitigate this, they do the same thing with Kas that they did with pHs. We don't use the actual values for our Kas all that much. Instead, what we use to rate the strength of individual acids is a value known as pKa. And just like pH was the negative logarithm of the concentration of hydronium, pKa is the negative logarithm of the Ka. All right? And this really is the gold standard for rating how strong an acid is. So, sorry, I just need to clear a little room. Oops. There we go. So for a pKa, the smaller the pKa, the stronger the acid. All right, smaller pKa, stronger acid. Larger pKa, weaker acid, all right? And in addition, it's logarithmic. So, for example, water has a pKa of approximately 16. Acetic acid has a pKa of approximately 5. So of these two, if I were to ask you which one is stronger, the one with the lower pKa is stronger. So acetic acid is a stronger acid than water. But notice, that we're dealing with 11 units here. 11 units on a logarithmic scale. Every jump down by 1, every move down or up by 1 is a power of 10. So acetic acid excuse me, is 10 to the power of 11 times stronger. And that's because it is 11 units. There's an 11 unit gap between water and acetic acid on the pKa scale, all right? So every one space is a power of 10. So 10 to the 11th times stronger. It's dramatic, all right? So that is how you rate the strength of an acid. You look at the pKa. That's important for buffered solutions, which we're going to begin talking about now, and we'll wrap up next Tuesday. So let's talk about buffers. All right. So, what is a buffer? Might be a good place to start. A buffer is a solution that contains a weak acid and its conjugate base all right. It's a solution that contains both a weak acid and its conjugate base. Or I should say. The presence of both acid and base in solution allows buffers to resist changes in its pH. All right, so what a buffer is it's a solution that contains both a weak acid and its conjugate base. What a buffer does is it resists changes to its pH. Let's think about how. All right, so think for a minute. What causes a change in pH? All right, there's a question. What causes a change in pH? To answer that question, you got to know what the pH is. pH is equal to -1 times the logarithm of the molarity of hydronium, right? So something that's going to change the concentration, change the molarity of hydronium, is going to affect the pH. And we know that there's only one thing, or there's two things that affect the concentration of hydronium. And that comes from the self-ionization of water. Right? We have the self-ionization of water with the equation Kw is equal to the concentration of hydronium times the concentration of hydroxide. We know that changing the concentration of hydroxide will affect the concentration of hydronium, or adding acid, right? Adding base, which increases hydroxide, changes pH. Adding acid, which changes hydronium, will alter your pH. All right? So the answer to what causes a change in pH is this. The answer is adding acid or adding base. All right? And here's why. Here's why. Think about what happens when you add acid. When you add acid to water, HA reacts with H2O to produce hydronium plus A minus. And if you're adding hydronium, this will change your pH. Think about what happens if you add a base. If you add a base to water, a base is going to take a proton from H2O, turning it into hydroxide and the conjugate acid. If you add hydroxide to your solution, that is going to affect the pH because hydroxide is part of Kw, the self-ionization of water. So adding acid changes the pH by increasing the amount of hydronium. Adding base changes the pH, increasing the concentration of hydroxide. All right? Now watch what happens. Actually, I'm gonna set this up. I'm gonna set this up, and then we'll continue this discussion on Tuesday. Today's Thursday. All right. So consider this buffer. Consider a solution that is buffered with hydrofluoric acid, which is a weak acid, and its conjugate base, fluoride. All right? A solution that's buffered with HF and F minus. And this is where I'm going to set things up. And then we'll do this together next class. Use the Bronsted-Lowry definitions of acids and bases to write balanced equations for, all right, think about what happens if you add an acid to your buffer, and think about what happens when you add a base to your buffer. When you add an acid to your buffer, your acid, HA, doesn't get a chance to react with water. It instead reacts with the conjugate base. When you add base to your buffer, it doesn't get a chance to react with water. It reacts with the acid in your buffered solution. So see if you can write these two balanced equations, what would happen when you add acid to your buffer, when you add base to your buffer, and think about why this will not change, why the buffered system will resist changes in pH once you get these down. We'll pick this up next lecture. I'll be hanging out in lab. Office hours, drop by if you have any questions. If not, I will catch you after the weekend, and I hope yours is a good one. Later, dudes.